Hi guys, I thought I'd make a quick video. We had a lot of people who were out for the explanation of how to figure out the theoretical moment of inertia for their rotating apparatus. So I'm going to show you how I did it for this one. This is what my apparatus looked like, and as you can see it has two arms, two little wrench nuts at the end, and a long, tall cylinder. Here is the scale that I used, and one of the things I was really careful to do is to make sure that my scale was calibrated so that I could get precise values. So if you don't know how to calibrate your scale, this little button right over there, you can roll it back and forth, but you want to make sure that you have an exact value. And I'm going to show you how I did my calculations in case it's useful. Sorry about the transition, but there's not much to do. All right, so here is my lab book, and you can see that I've drawn my apparatus here. And actually, I've labeled my arms, and I know which arms are which because they have different amounts of writing. This one has no writing, this one has writing. So I'm going to call them arm 1 and arm 2. The way that I keep everything the same for every one of my runs is that I put my hanging masses exactly 1 centimeter for the end of each arm. And now I've taken all of the weight measurements for each of my arms. One thing I noticed, and I don't know if you noticed, is that my two masses were not exactly the same. And so I know which mass goes on which arm. You could always mark them if you need to be. I know the inner and outer diameter of my tube. Please don't copy mine. A lot of the tubes have different inner and outer diameters. And once I did that, I was able to do moment of inertias for each one of the pieces. So this is the upright tube, this is the interior and the exterior radius, and what you notice is that you have to take the average of them. So don't forget to square them before you take the average. That's the general formula for a hollow upright tube that is rotating through the center axis. That's the average of their squares. You multiply it by the mass. Don't forget to turn your masses into kilograms. And our upright tube has a very small moment of inertia. You should get something between 10 to the minus 5 and 10 to the minus 4 for your moment of inertia. My 2 point masses have to be calibrated individually, and the lengths of my arm are not the same. So be careful about that. You need to measure them and know where the inset is. So the length of this is where the point mass is and not to the end of the arm. And finally, I calculated the moment of inertia using our squared divided by 3, and those are my 2 arms. And you can see they're also not a very big number. Our biggest inertia are the masses at the end, and I reminded you that you should test this by moving the masses around and seeing what happens to the velocity. So when I add them up, I get a total moment of inertia of 0.02. For most of you, you're going to get somewhere between, I think the maximum you should probably get is 0.03. Obviously, where the masses are makes a difference. So those of you who have really long arms are going to have a bigger moment of inertia than I have. And those of you who have shorter arms are going to have a smaller moment of inertia. The length of the upright tube does not matter. You notice it does not come into the formula. So don't get confused just because you have a taller tube that you're going to have a bigger moment of inertia. And finally, double check and make sure that you've done your conversions properly before you're settled on your theoretical moment of inertia. I hope that helps. Bye.